We now take a more detailed look at the Lasso regression or the sparse regression and all of the interesting properties associated with L1 norm minimization. The motivation for using various types of norms arises from the definition of the LP norm, which is given here. As we already know, this allows us to define a valid norm whenever p is greater than 1. But this definition actually does not prevent us from setting p less than 1. It would not be a norm for that case, but this quantity can be calculated nevertheless. In fact, we have already seen the shape of LP norm balls in 2 dimensions. So extending that idea, the level sets of this quantity for p less than 1 would look something like this. From this we can see that for the limiting case, as p tends to 0, we get the 0 norm of x, which again is not a norm, but turns out to be the number of non-zero entries of the vector x. So in summary, the L0 norm is a non-convex function that measures the number of non-zero entries of x and could be very useful in measuring the complexity of a model. The number of non-zero parameters in the model is usually a very good measure of its complexity. The L0 norm also motivates the L0 norm regularized least squares problem, where the goal is to obtain a solution with many zero entries. Here for a large lambda, since we are minimizing the L0 norm of x, we end up penalizing the solutions which have lots of non-zero entries and instead choose sparse solutions or solutions with many zero entries. Interestingly, the L0 norm does not depend on the value of these non-zero entries of x. Note of course that the L0 norm is not a norm but a non-convex function of x, and hence the L0 norm regularized least squares is a non-convex problem and difficult to solve in general. An alternative that has been widely used is to instead consider a convex approximation of the L0 norm. Now recall that LP norm balls for p less than 1 are not convex, but we can see that they can be approximated with the L1 norm ball. So instead of using L0 norm penalty, the closest approximation which is convex that we can make is the L1 norm penalty. But the question that arises is that while L0 norm penalty had all those nice properties and it yielded solutions that had many zero entries, does its approximation have any of those properties? So why should we not use L2 norm instead? What makes L1 norm such a good approximation? To see this, consider again the two-dimensional case with no noise. That is, let us say that y is equal to u transpose x. Now geometrically, remember that the constraint y is equal to u transpose x is a line. So we must choose x along this line. We can also plot the contour or the level curves of the objective function in this. So we can plot the level curves of LP norm of x. The level sets of the L2 norm look like these circles, and we are required to find the circle with the smallest radius. On the other hand, the L1 norm level curves look like these rhombus, and we need to find the smallest rhombus that intersects with the straight line. Interestingly, this picture demonstrates that most of the time, the straight line that intersects with the smallest rhombus does so at one of its corners, which lie on one of the axes. That is, the solution of the L1 norm minimization problem subject to this linear constraint is such that one of its entries is 0 and the other one is non-zero. This intuition is actually true even for higher dimension problems, while we can see that no such property holds for the L2 norm minimization, where the solution has both x and y coordinates as non-zero. So intuitively, even though the L1 norm was only an approximation of the L0 norm, the fact that it encourages sparse solutions with many zero entries remains. In the three-dimensional example here, we can see the same property holds. The constraint y is equal to a transpose x is now a plane that is required to intersect with the 3D sphere or the 3D version of this rhombus. Again, we can see the sparse solution is along one of the axes is obtained in the L1 norm minimization case. which is also the case when we are minimizing the L0 norm. Another way to look at it is that if the original x was sparse, then the L2 norm minimization problem returns an x whose entries are small but non-zero. On the other hand, the L1 norm minimization returns x hat whose non-zero entries are large but has many zero entries. Before we conclude, let us look at the use of lasso for the purpose of selection. We begin with the observation that when we are considering a solution X which is sparse, we are essentially only paying attention to the columns of the corresponding matrix A corresponding to the non-zero entries of X. This can be visualized by this cartoon here, which shows that only 3 entries of X are non-zero, and therefore Y is formed by linearly combining the 3 corresponding columns of this matrix phi. In other words, picking a sparse X is like discarding most of the columns of the matrix phi and keeping only a few. If the columns of matrix phi encode the features, then we are essentially selecting the features that can reasonably describe our observations while discarding all other features. To see this, consider a simple example where we want to determine the major risk factors for diabetes. For that purpose, we want to find out which columns of the feature matrix are relevant and can describe our observations. So let us say that we observe the insulin levels of these 442 patients, and we postulate that the insulin levels might be explained using a combination of factors that include the age, sex, BMI, blood pressure, and bunch of serum measurements. But we are not sure which of these factors are important and which are not. So to begin with, we keep all of them into the matrix A. Then if we apply the lasso to this problem, we will not only be able to obtain X such that Ax is equal to Y, but additionally we will obtain the factors that are actually important, because those are the ones that will have a non-zero entry in X corresponding to them. In summary, we can see that the sparse X may be required not only when we are interested in obtaining a parsimonious or a simple model, but also when we want to carry out a feature selection in a data set. So that is all about L1 norm minimization and its properties.